Now we can start. Okay, here. Hello, good morning, good afternoon, good evening, everybody. Welcome to the second part of InSAR for the built environment. So my name is Zhong Lu from Southern Methodist University. I'm honored to chair with my good friend, Dr. Alexandra Friday from TRE Art Major to chair this session. So I want to ask each of the speaker to talk about 40 minutes, 30 minutes, and wrap up things in about 14, 15 minutes. And ask for the audience to input your questions through the chat box, through the Slido. And if you are to the question to the particular speakers, and we will have a final 50 minutes to discuss all the questions, answer questions. Now, Alexandra will introduce the first speaker.
Morning. Good morning, everybody. Good morning. The first presentation is about the use of multi-temporary InSAR data for monitoring tunneling works, and will be given by Valentina Macchiarulo. Please, Valentina.
Hello, everyone. I hope you can see my presentation now, and welcome everyone to my presentation. My name is Valentina Macchiarulo, and today I'm going to present how we can use InSAR deformation time series for the assessment of structural damage caused by tunneling excavations in urban areas. Well, modern cities are growing faster and faster, with many more people living in urban areas every year. And to reduce surface traffic and improve air pollution, there is an increase in development of underground infrastructure in urban areas all over the world. The realization of underground infrastructure involves the excavation of tunnels. However, side effect of tunneling activities, they always produce underground movements, and these ground movements can damage the structures, the building adjacent to the excavations. In the worst case scenario, they can lead to the formation of big cracks to the surface of our buildings. In big cities, these large underground projects can involve the excavation of tens, even hundreds of kilometers of tunnels below the built environment. This means that the number of buildings that is potentially affected by the excavation is huge. Well, to protect our buildings, we could use some monitoring. And traditionally, monitoring involves the installation of sensors on the surfaces of the building that we would like to monitor. However, if you can see from this picture, the number of sensors that we need to monitor a single building is pretty high. And as these sensors are very expensive, the construction industry usually tries to minimize project costs and decides to include only a limited number of buildings in the monitoring scheme. This means that for most of the buildings along the excavations, we won't have any availability of monitoring data. Well, to assess the damage caused by the damage caused by the excavation in urban areas, we need to quantify some settlement, the building settlement. But as the monitoring data, the availability of monitoring data is limited, the settlement is traditionally conventionally quantified analytically using a greenfield assumption. This means that the settlement that is actually estimated corresponds to the settlement that we would have in a condition in which there is no building above the ground. Unfortunately, when there is a building above the ground, the real settlement profile is quite different. And this greenfield approach corresponds to the most conservative case that we would have. So this means that the assessment that is performed with the greenfield approach usually leads to conservative results. So it's very important to try to be able to quantify the actual deformation. Well, multi-temporal InSAR could come extremely handy for this application for several reasons. First of all, because it can provide data for very large areas. We know that it's extremely effective in urban areas. It can provide measurement for millions of measurements for buildings and other structures. And we know that thanks to the recent advantages of SAR sensor, we are able to reach very high spatial resolutions, meaning that we can collect high number of measurements also for a single building. And finally, lastly, very important is that the accuracy of this measurement is comparable with the accuracy of ground-based monitoring instruments. Well, so this seems great. However, the deformation itself doesn't tell much about the condition of a given structure. For example, a large displacement not necessarily produces damage into buildings. So in order to understand if a certain magnitude of displacement produces some damage or affects the structural condition of a given structure, we need to integrate the deformation measurement with some structural analysis. Well, here comes my research and my role. We developed a new method that uses InSAR deformation measurements for the assessment of building damage caused by tunneling excavation in urban areas. This method is based on an automatic workflow, and this automatic workflow takes 3 data sets as an input. We use a GIS database of buildings, we use InSAR deformation time series, and we use some data related to the characteristics of the tunnel and the soil in which the tunnel is excavated. So the building data, the building geometry is combined together with the InSAR deformation to extract the percentage scatter belonging to the building, and to make sure that the scatters belong to the building and not to the ground, we apply the threshold elevation and include in the analysis on all the PS that basically are located 5 meters above the ground. Then the line of sight deformation of the PS is projected into the vertical direction, and this information is combined together with the tunnel and the geometry on the soil to estimate the actual building settlement profile. And then this settlement profile for each structure is analyzed in combination with the geometry of the building through a very simple structural model to infer some critical strains for each structure. On the basis of the building critical strain, the structure receives a level of damage, and this level of damage are used to produce damage maps. Well, here we can see the InSAR deformation measurement that we use as an input in the developed method, and this cumulative displacement map was obtained by processing 72 Cosmos Climate images acquired between 2011 and 2015 from descending acquisition geometry. And each dot indicates MPS, and we use the conventional visualization with orange and red scatters indicate negative line of sight movements. And the most interesting thing is this slide is that everyone can clearly recognize the settlement that occurred in the center of the image after the excavation of the tunnels in this part of London. Well, let's try now to see how actually we estimate the actual settlement profile using the InSAR deformations. Well, if we look to the image in the top right corner, we see we're looking to a single building, and we're looking to this building from the top, and the tunnel center lines correspond to the dashed lines that we see here. The section, this continuous line, corresponds to a section orthogonal to the tunnel center line that we call transect. If we go back to the main figure, we're looking to the same building, but from the transect. So let's assume that we are projecting the building along the transect and all the PS as well. The dashed line in the main figure corresponds to the greenfield settlement, so to the profile that we would estimate analytically without having any monitoring data. We projected the line of sight displacement to the vertical direction to infer projection the vertical displacements, and this vertical we interpolate this vertical displacement using a modified Gaussian function that is based on the greenfield settlement profile previously calculated to retrieve this continuous line. This continuous black line corresponds to the actual settlement profile of the building. The proposed method was applied to the Crossrail case study in London, UK, and the Crossrail project involved the excavation of 21 kilometer twin tunnels. The tunnels were excavated up to a depth of 40 meters, mainly London clay. Each tunnel was characterized by a diameter of 7 meters, and the area in which we are focusing in this presentation is the area comprised between the station of Paddington and Liverpool Street. So here we can see the buildings in the monitoring area. The monitoring area was a case study of high interest for us because it was extremely rich of building with different characteristics in terms of both construction material, types of foundations. And why was interesting? Because we were able to use the output from the damage assessment, from the InSAR-based damage assessment, to infer relationships between the building characteristics and the building response to the tunneling. If anyone is interested in more details about this part and about its results, more results are available in our paper. And here we can see the same buildings now classified according to the density, the number of PS that we retrieve on each structure. So the reason for which we decided to estimate the distribution of PS over the monitoring structure is that we wanted to quantify how many buildings we were able to access with the proposed method and with the InSAR data set available. Well, and we defined 3 classes of interest. The reason for which we distinguish between yellow and green buildings. So we distinguish between building with more than 3 PS or with 1 or 2 scatters is that unfortunately for the buildings in yellow, even if we were able to retrieve some measurements, the number of scatters wasn't enough to perform a reliable fit. So actually we were not able to assess these buildings because in order to quantify the actual settlement, we need a minimum of 3% scatters per structure. So this is the results that we obtained from the assessment. So we were able to assess with this method about 860 buildings and quantify the damage for 860 buildings. The buildings were classified according to 3 levels of damage based on the critical strains that were retrieved for each structure. And category A indicates the lowest level of damage, while category C indicates the highest category of damage. And so in the previous slide, we saw the assessment based on the actual deformation. Now, just to give you an idea of what we would have got with the greenfield, so I compared here the outcomes of the result. So you can see that in the greenfield, 43% of building matched the highest category of damage, while with the InSAR-based assessment, when we quantify the actual settlement, the 38% of buildings matches that category of damage, meaning that about 5%, so about 46 buildings were actually put in the wrong category of damage when we use the greenfield-based assessment. So in addition to having quantified the conservatism of the greenfield approach, we demonstrated that this method can be actually used to improve damage assessment procedure, and we showed how InSAR deformation measurement could be used to complement ground-based monitoring instruments to assess the damage of buildings. And finally, thanks to this integration, was available for the first time a large data set of field observations on the building response to tunnelings. And thanks to this large availability of data, was available to infer new relationships and findings can be used to advance the understanding of the building response to settlements. Thank you very much for your time, and thank you very much for listening. As I recently started in postdoc in TU Delft, if anyone would like to contact me, please use this email address. And if there are any questions, I'm more than happy to take them later at the end of the session. Thank you very much.
Thank you very much, Valentina. And a quick recall that for whoever wants to address a topic, ask questions, please use Slido and put an @Valentina just to specify which speaker you are addressing your questions to. So I pass over back to Zong for presenting the second speaker.
Thank you, Alessandra. So the next speaker is Mahmoud. He will present about monitoring flood cycle stability of embankment dams. Now, Mahmoud, It's your floor.
Thank you. I hope you can see my screen and you can hear me.
Yes.
Yeah, great. So hello, everybody. My name is Mahmoud Haghighi. I'm a postdoc at the Institute for Photogrammetry and Geoinformation in Leibniz University, Hanover. And I'm going to talk about monitoring the stability of embankment dams in response to the 2019 flood event in Iran. So dam construction and in general, water management is a very controversial issue in Iran. Let me just give you a brief history of what's the problem and why that's very controversial, and then I can provide you some InSAR results on the stability of the dams and how they were affected by the flood. So Iran is a pretty arid or semi-arid country, and water resources are not distributed evenly across the country. If we look at the average rainfall map of the country, you see that, for example, to the north of the Alborz Mountain, here where we have the Caspian catchment, the area receives a lot of rainfall in parts more than even 2,000 millimeter per year. In the west of the country, where we have the Zagros Mountain, we have a fairly good amount of rainfall every year. But in contrast, in the Central Plateau catchment, which covers more than half of the country, we have a relatively lower rainfall. So although the Central Plateau catchment doesn't receive a lot of rainfall, it hosts more than half of the country's population, and it hosts most of the industries of the industries of the country. So there's a great demand for water in this area. So if we look at the share of water resources, both groundwater and surface water, we see that, for example, Persian Gulf almost has half of the country's water resources, but the Central Plateau catchment has only 30% of the water resources. So to meet the great demand in the central part of the country mainly, the demand is addressed mainly by groundwater pumping or by surface water diversion. There was a talk in the morning in the other session about how groundwater pumping affects many parts of Iran, but let's talk about surface water diversion. We have areas like here in the north of the country or west of the country where we have a lot of surface water. So in the past 80 years, many dams were constructed in these areas to mainly for different purposes. One purpose is to divert water to provide water supply for agriculture or domestic or industrial needs. Then some of the dams were mainly constructed for hydroelectric production, and some of the dams were also constructed for flood control. Here you can see a map showing the distribution of the dams across the country, and you see that many of the large dams are located here in Persian Gulf catchment. If we look at this small area, you see there are three different rivers here. We have Karkha River and Karkha Dam constructed on this river. This is the largest dam in Iran and has the largest artificial reservoir and was opened in early 2000. Then we have the Dez River, another large dam on this river. And then we have Karun River, which is the longest river in Iran and the only navigable river inside the country. So on this river, we have several dams constructed. Here we have Abbaspur Dam, then we have the Masjid Soleiman Dam, and then here we have the Gotvan Dam. So some of these dams, for example, Dez and Abbaspur, are concrete arch dams, and the others are embankment dams. And today I'm going to talk about the stability of these embankment dams, the Karkha, Gotvan, and Masjid Soleiman Dam. So mainly Karkha and Gotvan Dam were constructed for all purposes, water supply, hydroelectric production, and flood control, but Masjid Dam was mainly constructed for hydroelectric production and is not supposed to provide water supply or control flood. So let's talk about the large flood event in 2019 in Iran. So over the course of 40 days, in March and April 2019, there was a huge rainfall in Iran and it affected many areas. Here you see a map, 7 provinces were in need for humanitarian aid, and 6 provinces here, all in the Persian Gulf catchment, declared the state of emergency. So the flood cost around $5 billion and it killed 78 people, left more than 1,000 people injured, and in total it affected 12 million people. So if we look at again the average rainfall map of the country and the rainfall in only this period, when the flood happened in March and April 2019, you see that in many areas of the country, more than the average rainfall was received over the course of 2 months. So there was a dramatic rainfall. There was a huge amount of water here in Persian Gulf catchment inflowing to the dams. So the dams, the inflow to the dams increased dramatically. And if we look at the time series, for example, here you see in different years the daily amount of rainfall. There were some peaks in different years, but in 2019 or in late 2018, we had one peak, and then in early 2019, we had another small peak, and then in April 2019, we had a large peak of rainfall. So after these first 2 peaks of rainfall, the dams were the dams were filled, so there was a great amount of water in the dams. But the authorities were hesitant to release water before the 3rd peak because they were not sure how much rainfall they will receive, and the dams were supposed to keep water for the summer. So when they received the 3rd wave of rainfall, many of the dams were full, reached their limits, and there were a great concern about the stability of the dams. Here, if we look at the Sentinel-1 amplitude data from April 2018 and April 2019, I hope the animation works here. For example, in Karkhe Dam, we see that the area of the dam, and also I will show you some graphs later, the volume of the water inside the reservoir increased by 100%, so it doubled comparing to the last year. The other dam, Gotvan Dam, there was a 50% increase in the area of the dam, and in Masjid Suleiman Dam, we don't see much increase. As I told you, the dam is not supposed to keep the flood water, so any inflow of the water quickly is released from the dam. So after this flood, there was a major concern about the stability of the dams. Let's just talk quickly about the embankment dams and their structure. Embankment dams usually have a core made from impermeable materials like clay or concrete, and then the faces of the dam are constructed from earth or rock. So there are different deformations in embankment dams, most notably the settlement of the dam due to the weight of the dam itself. So after the construction of the dam, there's a settlement due to compaction. Then we have the water in the reservoir that has a horizontal force on the dam that can push the dam back, and then any increase in the volume of the dam, in the volume of the reservoir comparing to its normal, can have some excessive force on the top part of the dam. So we basically used in situ measurements from the Khuzestan Water and Power Authorities. They provided us the inflow and outflow measurements and also the reservoir volume. Unfortunately, the data is too short from April 2018 until April 2019. They cover very well the flood period, but they don't give us any information on the history of the reservoir situation before the flood. So to get some information about the history of the reservoir, we use Sentinel-1 amplitude data and estimate the area of the reservoir. We basically mosaic all images in each month acquired by Sentinel-1. Then we do a filtering on the monthly mosaic to get a more clear picture of the water, and then using a simple thresholding, we retrieve the water areas, and then after applying some morphological operation to get rid of these small areas, we estimate the area of the reservoir. So at the end, we have a monthly time series of the area of the reservoir. Comparing the time series of area with the volume, here on the left, we have the volume of the reservoir, in the right, we have the area. There is a strong correlation between area and volume. So it shows us that we can use the area estimated from Sentinel-1 amplitude as a proxy of the volume of the water in the reservoir. So we also do InSAR monitoring of the dams. I will show you some results from TerraSAR X Spotlight, which has a great spatial resolution of 1.5 by 1.5 meters in both ascending and descending. And then we have Sentinel-1 data, which is, of course, medium resolution. So for Sentinel-1 data, we use the whole archive. We produce more than 700 interferograms, and we do a full resolution SBUS. So here's a network of interferograms for SBUS, the coverage of Sentinel-1, as you see here, and the 3 dams that we study in this work. So here's the optical view of the Masjid Soliman Dam. It has a crest length of almost 500 meters and the width of 30 meters. Looking at the ascending interferograms from TerraSAR X, you see that the geometry of the ascending is not that proper for the dam. We have a lot of foreshortening, and as a result, the dam is kind of squeezed. So looking at the phase, we cannot retrieve much information. So looking at the descending data, it has a great geometry. Looking at 33 days, you see that there is a deformation going on the crest, and looking at longer temporal baseline, we see the main body of the dam having a huge displacement. So if we apply a multi-looking, for example, a 10 by 10 multi-looking, which is more or less similar to the Sentinel-1 data, we see that we start to do some signal aliasing. So it's important to keep the resolution of the data as high as possible when we process the data. So looking at the average rate of displacement from TerraSAR X, you see that there are 2 different displacement regimes, one on the crest of the dam, one on the face of the dam. And in the field, we can clearly see signs of such huge displacement. The rate of displacement is more than 13 centimeters per year, an alarming rate. And the results are from 2014 and 2015. So going to the more recent period, or the full archive of Sentinel-1 from 2015 until 2021, you see that we could capture both patterns of displacement on the crest and on the body of the dam. So thanks to the higher resolution of Sentinel-1 in the range direction, we could capture a lot of pixels. And plotting a time series for a point here on the face of the dam, you see that there's a displacement going on. I fit a quadratic model to the time series before 2019, before the flood. So here's the quadratic fit, and you see that after April 2019 flood, we see a clear acceleration in the time series. So looking at the volume and area, we see that this acceleration is correlated with the increase in the volume, but this volume change or this level of volume is not that surprising for Masjid Soliman. In previous years, we had higher volumes, but the main reason for this acceleration is probably that we had the volume increase in a very short, over very short course of time.
Mahmoud, you have 1 minute.
Yeah. So going to the Kalfa Dam, we have a much lower displacement rate. Plotting the time series, again, we see that we have the acceleration in the time series, correlated with the increase in the volume. So such a volume is exceptional for Kerkhoffs. For Kerkhoffs, it was the highest volume experienced by this dam, and we see the clear acceleration in the time series. And the last dam, Gotland Dam, again, we can retrieve the signal on the crest and on the body of the dam, and looking at the time series, we clearly see the acceleration in the time series. So to conclude, we can see that despite the medium resolution of Sentinel-1, it can provide a great insight into the post-construction stability of the embankment dams. But to retrieve useful information from the data, we had to do the single look analysis of Sentinel-1 data. So during the first 2 days of the conference, there was some discussion about ESO providing some user-ready data for such engineering applications. That end user will definitely need single look data. So, and even multi-looking the data might be misleading for the engineering community. So all the 3 studied dam in this study experienced post-construction deformation, and the concern about the stability of the dam after the flood was valid. And in future work, we have to do some numerical simulation to decide whether the post-flood acceleration was healthy or not. So thanks for your attention.
Great. Well, this is great talk. Alessandra, it's your turn.
Thank you, thank you. So we heard about the dam monitoring. Now we are passing a different subject, bridge monitoring using multitemporal InSAR data, and the presentation will be given by Chachu. Please. You should unmute.
Joshua, we cannot hear you.
Can you hear me now? Can you hear me now?
Yes.
Good morning. My name is Xiaochong Qing, and I am from Shenzhen University. My report is about the structure, health, monitoring for sea crossing bridges integrating time series InSAR measurements and structure principle. It consists of 4 parts. Firstly, the research background. Currently, the bridges are transferred from the construction to the maintenance stage. However, many bridges, especially the sea crossing bridges, usually affected by emergencies such as crash, vortex, extreme weather, overload, and so on. Their structural health are seriously threatened. This highlighted the significant demand for the structural safety monitoring of sea crossing bridges. Currently, 2 types of methods are used for the bridge monitoring: the regular manual detection and the automatic sensor monitoring. Although these methods are accurate, the complexity of the bridge structure and the survey environment would lead to the low spatial sampling densities, low operating efficiencies, easily damaged equipment, and so on. These methods are therefore not practical for the rapid and continuous deformation monitoring of the sea crossing bridges. The spaceball InSAR technique can obtain the large area surface deformation at all time and all weather conditions. With the low manpower, short revisit cycle, large coverage, and high precision, which highlighted the advantages of the InSAR technique for accurate and continuous deformation monitoring of large-span sea crossing bridges. However, there are still challenges that limit the InSAR technique for the high-precision bridge safety monitoring. Firstly, most previous studies focused on monitoring the highly coherent bridges and rarely involved in the partially coherent structures. Therefore, in this study, we examined the flexible cable stayed and suspension bridges with low coherence and which will exhibit greater vibrations and environmental factors. The scattering characteristics and the semantic information of the bridge, as well as the InSAR measurements, will be combined to improve the PT's density and to remove the background noise signals. Secondly, most previous studies identify the structural risk points only based on InSAR measurements without considering the different structural stress and deformation modes of the different bridge components. In this study, this would lead to high false alarm misdetection rates of the structural risk identification. In this study, the structural mechanics model will introduce for the mechanical property degradation analysis to improve the reliability of InSAR-based structural risk identification. In this study, the Stonecutters Bridge and Qingma Bridge in Hong Kong are chosen as our study objects. The ascending terrace and the descending Cosmos SkyMap images acquired from 2011 to 2012 are, as well as the Sentinel-1 images from 2015 to 2017 are processed in this study. These are the coverages of the 3 datasets and the static structures of the 2 bridges. In this study, the SAR coherent and incoherent information are combined to build a bridge foreground-background scattering model to enable the co-selection of the permanent coherent and partial coherent scatters. And these scatters, they will be subject to a refined denoising via the spatial temporal feature matching with the bridge structure semantics. Moreover, the distributions and the types of the backscattering signals are closely related to the observation geometry. The more closer the angle between the bridge direction and the SAR line of sight direction is to 90 degrees, the more likely the multiple scattering signals will be generated. Therefore, the single scattering signals will intuitively indicate the deformation of the bridge structure, which will, as this kind of signals will be observed in any observation geometries. Like most previous studies do, we firstly denote the locations with the large deformation velocities as the structural risk points. Moreover, distinct from the previous studies, the mechanic models of the bridge is introduced to improve the InSAR-based structural risk identification by removing some locations with large but elastic deformation that do not threaten the bridge safety, as well as adding some locations with the small but unrecoverable deformation on the significant load-bearing components. Then the results. Although the PT selected by the PSI method on the Stonecutters Bridge can almost cover the entire bridge, the PTs selected on the low coherence sections are sparse, and the background noise signals are also identified. By using our method, the density of low coherence sections increased and the background noise can be removed. This also verifies the feasibility and the effectiveness of our method. The results derived from the TerraX and the Cosmos SkyMap images showed highly consistent with each other. According the deformation profiles at different observation times indicate that the higher the temperature, the larger the deformation on the middle span. It is because the cables will expand at these higher temperatures, and the longer the cables, the greater the extent of this thermal expansion. Therefore, the deformation on the main span increases from the two towers and reaches the maximum on the middle span with the longest cable. The interferometry fringes also shows correlations with the temperature. And according to the further quantitative modeling, although the linear correlation are found between the time series displacements and the temperature, the correlation coefficient is not so high. It is because when the temperature difference is less than 10 centigrade, the thermal dilation is small and may be equivalent to the vibration deformation caused by the environmental factors. This will cause a decrease of the linear correlations between the temperature and the time series displacement. According to the mechanics model, although the deformation of the cable boundary points, tower beam junctions, and pier points are small, these points are also selected as the structure risk points because these are the main load-bearing points on the bridge. According to the Sentinel-1 time series displacements of the tower points, similar slight correlations between the tower points and the temperature are found. When the temperature increases, the towers expand, cause the tower points to uplift, and vice versa. The deformation of the middle span points also showed correlation with the temperature, but in an opposite way to that of the tower points. According to the maximum deformation differences, during the 2 years, we can see that the material property of the cables are weakening, while the material properties of the towers are stable. As for the Qingma Bridge, the PSI method fails to extract continuous PTs on the two low coherent sections. Our method can extract more continuous PTs on the low coherent sections, and the background noise signals can be removed. The results show the deformation velocity ranges of from -26 to 10 mm per year. The Qingyi Tower remains stable, and the Ma1 Tower showed slight subsidence, about -8 mm per year. The time series deformation profiles also show that the maximum deformation occurred at the middle span and also 150 meters east from the middle span. The interferometry fringe-based analysis are also consistent with the analysis of the time series deformation profiles. Also, a linear correlation between the time series displacements and the temperature are found, but the coefficient is not so high. It is because when the temperature difference is high, the total deformation is dominated by the thermal dilation. Therefore, the total deformation is highly consistent with the model-fitted thermal dilation. However, when the temperature difference is less than 10 centigrade, the total deformation is no longer dominated by the thermal dilation, causing the large discrepancies between the observed values and the model-fitted thermal dilation.
You have 1 minute.
Okay. And also, we can see the material properties of the towers are deteriorating, and no apparent mechanical damages are on the bridge towers. These are the deformation characteristics comparison of the two bridges, and the deformation property distributions of the pier points and the span points are similar to the normal distribution, but with slight variations, may be affected by the random and complex environmental effects. In this study, we constructed the foreground-background scattering model for sea-crossing bridges and realized about 40% improvement of PT's number, and also achieved the improved reliability of InSAR-based structure risk points of the two bridges, and achieved the bridge mechanical property degradation analysis, and also analyzed the deformation characteristics and the structure risks of the two bridges. This will enhance the power of spaceball InSAR methods and also provide an effective approach for the safety monitoring of sea-crossing bridges. That's all for the presentation. Thank you very much.
Thank you very much, Chacha. We can again ask any question using Slido, but I think it's time to pass to the fourth presenter. Please, Zong, the mic is yours.
Thank you. So the next talk is about validation of Sentinel-1 InSAR products for infrastructure monitoring, will be given by Sarah. Sarah, the floor is yours. Cannot hear you.
Sarah, can you unmute your mic?
Sorry, can you hear me?
Yes.
And can you see my screen?
Yes.
Okay. Hi, everyone. I'm Zara Sadeghi, a postdoctoral research fellow at University of Leeds. The project that I'm working on currently is funded by CDBB at University of Cambridge. And the topic is application of satellite technology for infrastructure monitoring. And one of our main goals is validation of Sentinel-1 InSAR, a product for infrastructure monitoring. I'd like to acknowledge my co-author, Professor Tim Wright and Professor Andy Hooper at University of Leeds, and Sakti Selvakumaran at University of Cambridge, and Sinan at University of Oxford. So basically, the advantage of InSAR for structural health monitoring is its capability to offer global coverage, remote access to structure, and also relatively low-cost monitoring. What is the goal of InSAR validation for structural health monitoring? It can help to improve acceptability of InSAR technique by the end user, specifically in the infrastructure community who are less confident about the InSAR technique, and also providing valuable input for InSAR development activities. Based on the definition by Terraforma validation project, there are two components for the validation. One is intercomparison of the results of different InSAR providers, which is called process validation, and validation by a comparison with ground truth, which is called product validation. So the application of InSAR for structural health monitoring largely has been done with high-resolution datasets such as TerraSAR-X, and due to widespread availability of free Sentinel-1 dataset that can be used in both academic and commercial environment, there is still a need to increase confidence about Sentinel-1 InSAR data for structural health monitoring. So we focused on validation of Sentinel-1 InSAR for structural health monitoring, and we've done the first component and published the results. You can also the result published in remote sensing of environment, and also you can see our poster, which is still available, showing the results of the first component of validation. And also in this presentation, we want to talk about the second component of Sentinel-1 InSAR validation. So our goal in this talk is comparing InSAR to in-situ observations, which can help to improve analysis by bespoke processing. What is our InSAR data set? So we process the conventional PS stamps method using Sentinel-1, and also we have access to SatSense data based on modified rapid SAR algorithm. So stamps is an open access time series toolbox. It selects PS using a phase-based criterion, and it improves PS density specifically in rural areas, and it's a single primary approach. And SatSense data is a commercial data. It selects DS pixels, and it improved pixel density, and it is based on a small baseline approach, and it has an efficient algorithm to add new interferograms. Our first case study is Hammersmith flyover in London. So it has 4 traffic lanes located west of London. It is a 622-meter bridge with 16 spans, and the 2 abutments are at the each of 15 piers. The general inspection revealed that there are concerns regarding the bridge bearing performance at multiple locations, and it is important to inspect bridge bearings regularly to make sure that they are able to move. So there are different independent monitoring systems that have been fitted to the bridge. One of them is LVDT, which measure displacement along the bridge at the bearing locations at each pier. Another one is temperature sensor, which embedded at 4 mid-span locations of the bridge. Here you can see the velocity map estimated by in A by stamps and ascending Sentinel-1 dataset, and in B and C using SatSense with ascending and descending dataset over Hammersmith flyover. I zoomed in Pier C location, which is clear in the figures. And previous studies showed that confirmed that temperature data can show an oscillating movement over a yearly period at each pier. And also LVDT data confirmed this sinusoidal oscillation on an annual basis. So the main source of displacement at each pier location is thermal dilation. In order to estimate this component, which is thermal dilation, in our stamps processing, we modified the phase equation to include this term, which contains thermal dilation parameter and temperature baseline, and we have access to the temperature, as I said, based on the sensors installed on the bridge. So in this figure, we can see some results at Pier C location. So A is showing the estimated line of sight velocity by standard phase equation in stamps, and B and C are showing the results of stamps after modification. So B is showing the velocity and C is showing the thermal dilation parameter. So basically from C, you can see that there is a noticeable signal of thermal dilation at Pier C, which is clear after modification of the phase equation in the processing. We also looked at SatSense data at the PRC location for both ascending and descending data set. And a comparison of these two figures confirmed that the displacement occurs in opposite direction, indicating that there is a noticeable horizontal movement at that location. In order to compare the time series of InSAR results at PRC location with LVDT, we had to convert InSAR line of sight deformation to bridge parallel orientation. We did this, and in this figure you can see comparison of the time series calculated by LVDT and also stamps using ascending, and also SatSense using both ascending and descending. So you can see that there is a nice agreement between LVDT and InSAR data here. The RMSE is better than 4 millimeter, and it can show that even using different geometries, which is ascending or descending, or different algorithm, the independent algorithm, stamps or SatSense, we can show a nice agreement with LVDT data. We also plotted this displacement along the bridge against temperature for both LVDT and InSAR, and also plotted the fitted linear trend to both LVDT and InSAR. And also we can see a level of agreement between the estimated linear trend from LVDT and InSAR from different geometries or different algorithms. Our second case study is bank station. So London Underground's Ltd's bank station has been upgraded to increase its capacity. The scheme is known as Bank Station Capacity Upgrade. 1.3 kilometer tunnels have been constructed as a part of modernization of this station. So the displacement induced by excavating activity had the potential to cause damage to important structures like mansion house building, which we focused on this case study. And also there are some different independent monitoring systems that have been installed on mansion house building. And we selected 3D prisms to compare with InSAR data and validation. Here you can see the estimated velocity map over bank using SatSense, both ascending and descending data set. Before comparison with comparison of InSAR with 3D prisms data, we solved the geocoding issue of the InSAR products. So the low resolution DM, which was used in the processing, failed to calculate the correct height for each InSAR pixel covering the building or surrounding roads, and introduced a geocoding, individual geocoding shifts for each InSAR pixels in range direction. So we solved these individual geocoding shifts using high resolution digital elevation model, which is a LiDAR DSM, with an iterative approach. And after solving the individual shifts, if there is any overall gross shift, it can be detected and removed from the InSAR dataset. So in our approach, for each InSAR pixel, we have the height from SRTM, which was the DEM that used in the processing. And also we can extract the height from LiDAR DSM and calculate the delta H and the corresponding delta range. and find a new location and iterate this process up to height or location convergence is achieved. Here you can see examples of 2 points over mansion house buildings. In the iterative approach, we try to find the intersection of the topography with the range line. For some of them, like the figure on the right-hand side, with iteration, easily it converged to the intersection with the topography. But for example, for the left-hand side example, we need to encourage convergence because of the non-smooth topography that we have around that pixel. So after doing the modification or correction of the geocoding issue, we converted the 3D data that we had access to line of sight and compare these data with InSAR data that we had access after modification. For some examples with ascending and descending geometries, these are some examples that you can see showing the RMSE less than 2.7.
Sarah, you have 1 minute.
Yeah, sure. So basically we validated Sentinel-1 InSAR in this research for different case studies with different source of deformation, thermal dilation, or tunneling activity, using Sentinel-1 InSAR data with different geometries, ascending or descending, and also 2 different and independent algorithms, SATSense or stamps, and also using different ground truth data, one-dimensional LVDT or 3D prisms data. And the RMSE value was better than 4 millimeter for Hammersmith flyover or 2.7 millimeter for mansion house building. And this validation helped us to improve the InSAR products, such as working on geocoding errors or a modification of the phase equation. So this research can help to increase the level of acceptability of Sentinel-1 InSAR for structural health monitoring. Thanks very much.
Thank you, Sarah.
No problem.
So, Alessandro, looks like, do we have the 5th speaker?
Yes, don't know whether Alan was
Okay.
able to rejoin because I know he had some technical issues.
Okay, he's reconnecting.
Okay. So, Alan, if you are now back, we'll be pleased to hear from you. And we change topic, passing from, say, the monitoring of civil engineering structures to the oil and gas world. So please, Alan.
Sorry, one moment. I'm giving the presentation on, sadly, Peter Lisenberg isn't able to join me, but anyway, the talk is really a technical discussion, a little, and then some examples in the upstream oil industry, and then a discussion. Really what I want to stress is that, there's a lot of people, there's an awful lot of studies done sort of retrospective, and I think there needs to be a move to get InSAR out into the industrial and commercial world. That's really the thesis of the talk. So first of all, the technical discussion about the details, how they're not really understood, in my opinion, outside of the space industry. And that really, I think, needs to change. So InSAR, as you all know, was developed in the 1990s, and it's a well-proven technology, thousands of technical papers written, PhDs granted. And but what I've found is that throughout, whenever we give a commercial presentation to someone that's not familiar with it, we can't say, well, it's well proven. We have to go through, this is what the satellites are. This is why, you know, we get the microwave signal in the sweet spot. It's not affected by cloud, the reflectivity, etc. All these studies in their own right, and many people have spent years on all this, and it's, you need all that in order to get to this end product. And so I think there's a need to refocus InSAR and move from the historical retrospective, tends to be, and I apologize here, I'm saying academia, but a lot of the studies that we read are sort of retrospective, they're reactive, they tell something, and there needs to be a move to prediction and proactive. Really, that's what the commercial customer, the client, wants. And you have to show clearly and cleanly the economic benefit, and then follow through and keep them involved. So I think we need to still evangelize about InSAR, and one's basic geoscience and engineering skills are very important to be able to understand where the potential customer and client is coming from. So I'll go into some examples in the upstream oil industry. I've changed from the sinkholes in West Texas to something in the Los Angeles, California area that might be, I think, more useful or more interesting. So when you're monitoring the performance of a petroleum reservoir, you need to think commercially. You know, the upstream oil company needs to produce as much oil and gas as possible, needs to be produced as cheaply as possible. And one of the keys, the main key to doing that is maintaining the original pressure by balancing the volumes produced by the volume with the volumes injected. But it's very difficult to do. And here, InSAR can help. The key thing is this voidage replacement ratio, VRR. And when the reservoir loses pressure, the reservoir will compact, ground level subsides, and you get negative deformation. If you over-inject water, the reservoir will expand, ground level rises. And of course, you can apply these concepts to reservoirs in general, aquifers, really any rock with porosity. And so from a commercial sales point of view, you have to be ready or able to move from, you know, if you're a petroleum geologist based InSAR type, you need to be able to move to another use for InSAR within your subject domain where you've got the expertise. So very luckily, the type example is Belridge Field. It's got three characteristics that make it excellent for InSAR studies. First of all, very high porosity. I mean, you can 55-65% is unheard of, except in diatomites, really. Very low permeability, really it's less than concrete. And for the InSAR purposes, It's in a semi-desert environment, so we have a great SAR signal. But the combination of the very weak compressible rock makes maintaining the voidage replacement ratio of 1 very difficult. So too much production, ground level goes down, too much injection, ground level goes up. But it's fairly easy to monitor. And even though there's continual compaction, there are spots within the reservoir where things go out of balance. And this is the field, 15 kilometers long, about 4 kilometers wide. And so you use InSAR to monitor the overall reservoir health, and you're looking for broad changes within the reservoir. And then you look for sudden changes, which will be these little spots here, maybe here as well, that's very rapid and has a smaller area. So what one of the operators does at Belridge is they use the InSAR to fine-tune their water injection processes. And what they do is they have a tuning process. They get the InSAR every 11 days. They quickly check for the anomalies that need quick action, and that we'll cover in the next slide, slide 10. And then they use the InSAR to cross-check the water injection. If there's a part that's risen up or deformed downwards, then they'll increase injection or decrease water injection. If the worst comes to the worst, they will cut back production if there's not enough injection water available. And for them, the result is increased oil production, a more evenly balanced injection, and fewer problems due to operating instabilities. The people in the field are not turning the valves on and off multiple times and causing other sorts of problems. So there's also the smaller anomalies due to the reservoir compacting. And if the reservoir compacts, the casing in the center might crimp. There's all sorts of shearing zones set up in the shallow overburden, surface fissures, etc. And anything escaping from the reservoir is bad news, and it's an indication of poor operating practices. So InSAR will also pick up these, and this particular one here, 400 meters wide, in an 11-day cycle, 2 centimeters uplift. That was cured by examining the wells in this area, fixing the bad actors, and with the next pass, the whole blister, as we call it, compacted back to where it was before, and you get a negative here, which really is this collapse back. And I think InSAR encourages being proactive and provides the ESG assurance that the stakeholders need in their a permission given to the operator. And now quickly on to Los Angeles, city of 10 or so million. It's also got groundwater basins, a lot of landslide areas, and major activities going on. Plus, it's the U.S. second largest port down in this area here, and right in this area is a big oil field, and I'll go down to this little map. It's the Wilmington Oil Field, and there are 3 offshore artificial islands here with directional wells. But you also have a strand of the San Andreas fault here, the Newport-Inglewood fault. You can see there's a difference from one side to the other. There's a landslide here. There's a water basin here that's probably going down, and I mean, it's somewhat cyclic. But these are all things that need to be looked at commercially. So you landslides here, for example, especially after the heavy rains, which it doesn't rain much, but after wildfires, the ground gets easily washed away with rains and a lot of landslides. There's also subway tunnels being put in, and that's a case of ESG assurance for the local inhabitants. There's also water and sewage pipelines to be monitored, just for EHS purposes, but also if you were living there, you would want to make sure that nothing was going sour on you. And InSAR engineers are needed for all of this. So, and as everyone knows, SAR data now covers all onshore geological basins. It's readily available. But looking towards the future, you know, there's more satellites going up, seems like every few months, more frequent revisit times, eventually maybe hourly or every few hours. And it's going to be a commodity product. It's going to be cheap and maybe even free. And so for a commercial InSAR project and for the InSAR engineers working on them, you need to see the value of prediction. You know, you use the past data to set the, you know, your background, but looking forward, you know, you can help the commercial, the financial side of whoever your client is.
Alan, you have 1 minute.
So anyway, I think that's about it. Appreciate you listening, hopefully open-minded and receptive. Please, any comments, just get in contact with either of the authors. And of course, if you're interested in a commercially oriented career after your studies, please contact us as well. So thank you.
Thank you, Marco. Thank you. So from very technical presentation about civil engineering, we pass to a very nice, say, wrap up of the situation of InSAR in the oil and gas patch. Much appreciated.
Okay.
Now, the floor is back to you, Zong.
Thank you, Alexandra. So I think we have some questions. I think now is the time to entertain these questions. I think we go from the, in the sequence of the speaker, so that the speaker can take a look at questions. I think we, each of them use 2-3 minutes, and so that everybody have a chance to answer some questions if we have remaining time, and then we can continue to on more of the questions. Valentina, it's your turn. You have a lot of questions from you. Maybe you can read some of the major questions you want and then answer them in a way.
Okay. So someone asked how we can actually link the PS to how we link in our method to the buildings, and yeah. So actually, the way in which we do it is simply using the footprint of the building. So we use the coordinates of the PS to identify basically the building that fall within the PS footprint. And then the information, the elevation is very important because we know that the geolocation of InSAR is at the order of meter depending on the sensor. But so so that's why we use the information, the elevation, to make sure that the PS that we are using in our analysis are actually belonging to the building. And of course, we try to be conservative on the threshold on the elevation because we wanted to make sure that the PS were actually belonging to the building. So probably we might have missed some of them. And I hope I respond to the question. And the other one is which type of building we have considered and if we perform any non-destructive testing techniques. So, the building data that we used were mainly information about the construction material, the type of structure, and the foundations of the building. These were the information that we used for the analysis. And we didn't use any NDT techniques for our study, but the material parameters were estimated, were based on knowledge on the buildings in London. And if more detailed information available using external techniques that could be easily introduced in the algorithm. And someone has asked, not sure if this one is for me only, anyway, I will reply. Someone has asked, how important is the resolution of data for monitoring small building, and we cannot the sensitivity and measurement with different incident angles. Well, the resolution is very important because and that's why we put ourselves in the best situations possible. So that's why we start with Cosmos that offers a very fine spatial resolution. And so we want to be able to geolocate the HPS the better as possible. So that's why. And the other thing that is important when we analyze a case study involving tunneling is that we consider the line of sight satellite incident angle, but we also take into account the characteristics of the tunneling, so the depth of the tunnel and the width of the tunnel. So we have to select the sensor taking together all these characteristics. And I think someone asked why we selected a criterion with 3 or more scarcity factors to actually perform the assessment if we consider approaches. So, well, the need to use 3 scatters was related to the fact that we could use a different approach. So the one in place is a more general approach, but in our case, we were doing a very specific assessment in which we wanted to quantify the curvature of the settlement. And if you have only 1 or 2 PS, you can interpolate the points and estimate of curvature, because if you have 2 scatters, you can have a straight line and maximum. But since we wanted to quantify the curvature, that's we needed at least 3 scatters, basically. And I think last one is probably comparison with damage map is the PSA InSAR line of study action. What parameter variable used to convert InSAR data into building damage category? So the parameter that we use to convert, we didn't use the damage map is not based on the line of sight measurement, but it's based on the projection of the line of sight measurement on the vertical direction, because this is the information that is important, is interesting for tunneling. And the parameter of interest was the deflection ratio of the building, basically quantify the tilting of the building associated with the settlement. And this was the information that we quantified and used to determine critical strains and then identify the level of damage to the structure. I hope it replies to the questions.
Thank you. Thank you. Now, I think, Mahmoud, you have a couple questions for you.
Yes, sure. There are 2 questions. The first one is, how important is the spatial resolution of the data for dam monitoring? And the second one, do you think it's more important, the spatial resolution of the data or the temporal frequency of the observations? Well, the spatial resolution, as we have seen, is really important. For example, with pterosaurids, with that high resolution, we could retrieve a lot of information, but basically there are different types of dams. The type of dam that I have monitored here in this study were all embankment dams. But there are different types of dams, like concrete arch dams. For those dams, of course, the spatial resolution is extremely important. So it wouldn't be possible to use Sentinel data. I have tried to do some analysis on some of the concrete arch dams, but mainly because of the medium resolution of Sentinel-1, it's not possible to retrieve any useful signal for those dams. So for such dams, it's extremely important to have high resolution. But on the other hand, for embankment dams, if, for example, in the case of Masjid Suleiman, we have a high gradient of deformation, a high resolution but low temporal, a high spatial resolution but low temporal resolution would not help that much. So it's also important to have a high temporal resolution like Sentinel-1, and in that case, we could retrieve, I mean, because we have like 5 meters of resolution in range direction anyway, so we could retrieve a lot of information for the dam. So I would say both are important, and beside the resolution, you also need to take into account that the geometry of the dam is also important. So not all the dams are great to be monitored by InSAR. Yeah.
Thank you. So, Xiaoqun, you have a couple of questions too.
Okay. Firstly, what leads to existence of low and high coherence sections on the same bridge? For example, some features of structural geometry or materials or something else. According to my experience, firstly, the material would lead to the different coherence sections. For example, the steel structured bridges tends to show stronger backscattering and higher coherence in SAR images, maybe than the concrete structured structures. Moreover, the structural characteristics is also a significant factor. And for example, taking the examples in our study for the cable-stayed bridges, the tight steel cables, towers, and decks of a cable-stayed bridge constitute a three rigid piece, stable and unchanging system, whereas the main cables, towers, and decks of a suspension bridge would constitute a variable system. Therefore, the suspension bridge would exhibit more silvery vibration and lower coherence than the cable-stayed bridge when exposed to the complex environmental loads. And finally, I think the observation geometry would also have some effects, but I'm not sure. Because for a bridge section of a given length, the longer the projection along the flying direction, the longer the SAR observation time will be, and may result in more information being extracted on the structure. Therefore, I think the angle between the SAR line of sight and the bridge orientation would also have effects on the coherence. And secondly, how to improve the point density along the bridge and how to separate the single, double, and multiple scatters. In our study, the SAR coherent and the incoherent information is fully combined. The coherent information comprises the total temporal coherence of the PSI interferometry dataset, and the incoherent information comprises the statistics of backscattering signals, such as their average intensity and amplitude deviation, are used to select the permanent coherent scatters on the bridge as more as possible. And then the partial temporal coherence of the sparse interferometry dataset is also used to minimize the effects of the decorrelation, making the partially coherent scatters also being detectable. Given the more silvery vibrations experienced by the low coherent structures, the larger amplitude deviation and vibrating noise tolerance are set to maximize the number of detectable partial coherent scatters. But we have to carefully balance the number of PTs and their reliability. As for the separation of the single, double, and multiple scatters, actually there are not so many good methods currently, maybe except for you can use the Tomosar technique, but we didn't do it. We separate them according to the observation geometry analysis of the specific bridge. Through the visibility analysis of the bridge structures, we can infer the different geolocations, elevations of these scatters. And moreover, we can also identify the single backscattering scatters by integrating multiple datasets with different look angles, because we think the directly reflected single bounce signals can be observed in most observation geometry conditions. Therefore, in our study, mainly based on the post-spatial temporal feature matching and semantic analysis. Thank you.
Thank you, Hitu. I think we have a question for Sarah and one question from Malcolm as well. Sarah.
Yes, yeah. The question is, how far was your reference point compared to the bridge when performing your validation? Did you change the distance of the reference point from the bridge? Yes, actually the distance of the reference point to the area that we worked on for is very important for specifically for comparison with ground truths. So for the bridge, for the Hammersmith, I think I selected the reference point in a less than a 100-meter distance from the bridge. And also for the bank, I selected the reference area outside the deforming zone and again, very close to the area. So definitely selecting reference area very far from the case study can affect the results of comparison, specifically because of the atmospheric effect.
Thank you.
No problem.
Malcolm.
Yes, we had a quick question for Malcolm about the possible impact of InSAR data on fracking operations.
Yes. So at the Belridge field, the wells in the diatomite go down to about 600 meters, and those that are fracked, with the fracking operation only lasts a few hours. Maybe for a big a long well, maybe a short horizontal well, maybe half a day, and so it's very difficult to observe a frac. I think with more satellites and faster revisit times, and with in West Texas in the Permian Basin, where the long laterals are maybe 10,000 feet or 3,000 meters. I think maybe once there's a one-day revisit time, I think it's going to be possible to observe the ground being inflated. But currently, no. And of course, as an aside, in California, it's almost impossible to get approval from the government agencies to do a hydraulic frac. And so that's another problem. Stakeholder engagement, EHS is becoming way more important within the oil industry now.
Thank you.
And again, InSAR can help with that.
Thank you.
That's great. Thank you all for this very lively discussion. I think we talk about spatial temporal, we call it one high temporal resolution, high spatial resolution. I'm actually, I have a question. Do you guys have thought about how to increase the spatial diversity, you know, to do the topo SAR, that kind of stuff. So let me say, for the infrastructure monitoring, you like the high resolution, high spatial resolution. What else do you need?
I think we all agree that we need to go for high spatial resolution for civil engineering projects, but we need also high temporal frequency of the observations if we want to create very reliable results to then pass them to the civil engineer or the oil and gas community. So for sure, it's an open question, and I would recommend everybody to really try to attend the session tomorrow, where we will try to discuss together with ISA in details also possible strategies to improve, increase the amount of data we can get, not only, of course, from Sentinel-1, but in general, also thinking about future observations. So thank you. I think this would conclude our session today. Great thank to all speakers and of course to Professor Liu. And again, see you soon, hopefully tomorrow for the technical discussion. Bye-bye now.
Thank you all.